Welcome back to the bench. In this episode, we have two function generators, and I managed to pick these up a little while ago. Both of them have been sold as non-functional, and so we're going to take a look at to see what's wrong with these generators and see if we can repair them. The one on the right, I've already done some initial checkouts on, and I've noticed some problems with it. The one on the left, probably will be using as a parts donor initially, and then I'll come back and reload the parts back in and then do diagnostics on it. These are Hewlett-Packard 3314 function generators. Very unique little animals in that they're essentially a completely analog function generator, and they have a very simple premise to them. At their core, they're nothing more than a triangle wave generator using two different charge and discharge current sources, or current source and current sink if you want. And by changing the capacitor that's charging and the current that's going into and out of the capacitors, the frequency of that triangle wave, and as well as the envelope of the triangle wave, or the skew, can be adjusted. And then from that triangle wave you can generate the square wave and the sine wave as I believe it's a third harmonic. So let's get on with it. I think the first part of this teardown and diagnostics will be on the one on the right. And it's indicated by a small defect on the screen here. You can see that little bit of a diddly-do in the screen printing. And we'll see how hard it is to repair these units and get them back functional again. Just as an aside, before I move on, I'd like to acknowledge that the channel has surpassed 100 subscribers. I mean, this doesn't seem like a lot to most channels. I'm kind of surprised myself that it's reached that far. I've just described and kind of designed the channel around being an open, kind of like a university premise, where anybody that's interested in learning something can just drop in and listen in, and if they're interested they can maybe stick around and listen for future things on the same subject. I am planning on trying to make the channel a little bit more broad in terms of what I'm doing. So I've got a couple of projects coming up that'll involve more modern electronics, microprocessors and firmware design, as well as getting in a little bit more about how to engineer or design a new project from the ground up. So without further ado, let's just step on in and get into this project at hand and see how far we get. This is the first unit. Just to let people know, I've already done quite a bit of work on it, so you will see some non-standard stuff when I take the cover off. I'm just going to show just general disassembly tips on how to get the covers off and how it actually all comes apart. It's a bit unusual on this model. I guess HP were starting to figure it out, because they kind of standardized on test equipment later on. So the first thing you want to do is actually take the handle off. The handle is actually the way that the top is secured on here. There are two end clips. So those are just unscrewed and they're just removed. I've already removed them. The back clip just pulls off from the back. Like so. It has a plastic there, so be careful not to break it. And then the handle's off. At this point you should be able to pull back on the cover and get the top off. Slide it off the end. I'll put that away somewhere. So that's the top part, and as you can see I've already been in here and made some changes. Swapped out some caps and made some cable replacements. I'll talk about them a little later. The bottom of the unit has a screw hidden here. It may be behind a label or something. You would want to unscrew that, and that will partially pull the bottom out of its cover on the front. And as the screw is extracting, it's captured in the bottom piece, and so it will pull it out from the front, and then you can keep on pulling on it and pull the bottom of the cover off. This is the heart of the machine. Under this shield is where the waveform is created, and it's then shaped as well. Triggering, synchronizations happening over here. A lot of analog operations on this board here. This is the output board, the driver board, where the signal is actually finally amplified and buffered. And this is the attenuator relays for changing the amplitude of the signal. The top board is the processor board. This is the main microcontroller. This controller over here is responsible for the GPIB port, so that you can hook up another external computer and program this unit to perform automated tests. The machine is designed partially for the purpose of using it in an automated test equipment, or ATE. So it's an interesting little thing to play around with if you want to get into the, not GPIB, but the HPIB protocol. There are 3 screws holding this shelf down. I've taken 2 of them out. I just have the central one in the middle to remove. Pay attention to the cabling here in the back and the power cable here. Sometimes it gets trapped by the board. Then the unit has 3 hinges in the back, and it just swivels up like that. It can only go about a little less than 90 degrees. So if you want to hold it up, I suggest maybe getting a stick of wood or something and propping it in here to hold it up. It kind of will stick a little bit, but I wouldn't count on it staying up there. I've done a couple of things to fix this unit. First of all, I've just taken the caps, these larger electrolytic caps, and just replaced them with a newer style. Regardless of how the condition is on these things have a rated lifetime in terms of hours, so I find it's just a little bit more peace of mind for me to just put in new long hour caps, and these are designed for test equipment for high hours usage. In this particular unit, I found some problems with the power supply. There was some dipping in the rails, and I believe the other unit will have the same issue. These 2 transistors here, which are actually screwed into the side of this heatsink on the inside, are using a 3-position connector here to connect them to the board. So the transistors are not soldered to the board, they're just using a 3-pin connector. This is what I believe is an Amphenol style connector. They were gold plated, but I did find that the leaves, the spring leaves on these had weakened, as well as had actually corroded a little bit. Once I'd cleaned the transistor legs and replaced them, these white ones are actually new units I got from DigiKey. This is the existing, or the old unit or connector that I removed. And I did pull the leaves, the spring pins out, and re-straightened them and polished them. And it was working, but I decided just to ensure that it would work in the future, I'll just replace them with new ones. So this is for the minus 15 volt and the plus 15 volt regulation, which is a linear regulator. This larger transistor is used as a switching resistor for the 5 volt power supply, which is a very funky, interesting little switching power supply. It actually uses a 555 as its function generator, as its pulse generator, running at around 33 kilohertz to generate the 5 volt output. Main power input is here, main rectifier, and this is the plus and minus 24 volt power regulation. Of course, 5 volts takes its power off of the plus 24, so that's supplying both plus 15 and plus 24. But there's not a lot of current in the plus and minus 15. It's the plus 5 that's taking the brunt of the current. This unit had a lot of problems with the front face. The output of it was very inconsistent and flickery, and it wasn't really working at all. I couldn't get a good consistent output on it at all. This was the original cable that was in this unit, and I found that what was happening here is that the internal conductors in this ribbon cable were separating at this point, and if you take a look at the cable, you can see that there's a lot of separation in here. The laminations have come apart at this point, probably because this is a high stress point where the unit is being serviced. It will have its lid up, so this is constantly being flexed as the lid's being removed, and so on. So for over the years, this has just become a very inconsistent and unreliable connection. So I just hopped onto DigiKey, found some little press fit connectors, and I had some cable lying around, so I just created this cable, and I just punched them down into the connectors. The cables are 16 position, so it's just a matter of finding another 16 pin, 0.1 inch spacing, standard 0.025 post connections, and putting them on there. I also went ahead and took out the other 2 ribbon cables, which mated the processor board to the other 2 boards. And as an aside, they're referred to as the A1 board, the A2 board, and the A3 board. I believe this is the A3 board. So this carries processor address and bus and enable lines to the other 2 boards for all of the digital parts of those boards, mainly things like DACs and ADCs and registers and latches. This connector here, you don't really need it unless you want to use HPIB support. This is the H connector to the back HPIB connector. If it's damaged, it's like, well, HPIB is not going to work, but you could easily run the unit with this removed, and it wouldn't really affect any of the front panel operations. A little word on capacitor replacement. You want to try to replace all of the electrolytic capacitors, the wet electrolytics that have this style, either axial or radial. What you don't want to replace are these little silver Sprague capacitors. These are actually hermetically sealed glass capacitors, and they are still working perfectly fine even today, and they'll probably work for the next 50 years. These things just never dry out. They're extremely reliable, very high, very precise capacitors. I measured a couple of them, and they're usually plus or minus 1 microfarad. Like, for example, these are 15 microfarad ones, and I'm measuring anywhere between 14.5 to like 15.5 microfarads on the value. ESR is also similarly very good. They're typically 0.1 to 0.15 ohms. I believe that's on a 1 kilohertz test. So just leave these alone. They don't need to be removed. There may be one that looks like a sealed capacitor, but it's not. This unit here, which I think was in here, in the back here, behind this choke, is not a sealed unit. It's just a standard electrolytic. It's got a rubber base on it. So go ahead and replace that. So that took care of the power supply inconsistencies and other problems. But I did have a problem when I lifted the board up. I would have a very inconsistent, and sometimes the power would just shut out and come back on again. You may want to go into here and just check the wiring in here. The wires can go hard and brittle, and they can start to crack. So you may need to replace a couple of them. And I've actually gone ahead and done that on a few of these connections. This connector here hooks up to a cable that goes up to the front panel connector, and it's actually this cable here. I also had a problem in here on this power switch. There was some very bad soldering in there. I took the switch apart and I resoldered it and just put more heat shrink on it. And now it's very reliable. I can move the lid up and down all day long. This power stays on, it stays in its present function, and it's perfectly fine. The main problem of this unit is it fails to calibrate, or fails to recognize that it's running at a certain frequency. It's having a problem, which is what I'm referring to as an E30 cal issue. When it's powered up, it displays E30 cal errors at all of the frequency ranges, and it just can't start up normally and run through a quick cal or quick test and then be ready for operations. So the next part of this will go into some details of that part of the diagnostics and repair. So after the power up, the frequency does work to an extent. As soon as you go out to the next range of frequencies, which is on the 2s, so you can see here that as I go from 1 kilohertz up through 2 kilohertz, you'll get another E30 range error or cal error. And then it jumps into the next frequency range. So what's happening here is basically the processor is trying to calibrate the frequency at the new range using a built-in frequency counter. It's actually counting the sync pulses, or trying to, internally. And it can't sense the frequency, and so what happens is it throws an E30 cal error. On startup, it runs through all the ranges internally on a self-startup test and tries to measure the frequencies, and that's why it's constantly saying E30, 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 E30 as it's switching through the different frequency ranges. I believe it also does some tests on different attenuator levels, which would be the amplitude. Not shown here in this scene is you can see there that it just immediately went to 0 millivolts. This seems to work a little bit better. These 3314 units, they're pretty hard to dial in the amplitude and frequency because you have to do everything through these three buttons here. There's no way to use the keypad, for example, to type in a frequency, which is a bit annoying, but it's just the analog nature of these old generators. So here's the bottom of the unit. This is again the first unit that I'm repairing, the one with the E30 cal issues. This is the output board with the two drivers, and these two matching transistors, PNP and NPN, form a totem pole type driver arrangement, and that is generating all frequencies that are coming out of this. This arrangement of relays is the attenuator section, and then the signal here goes to the front panel. This flips up. One thing I recommend is that if you're doing any repairs on these units and having to service them, remove this cable going to the driver board, the output board, and just put some contact cleaner in there. It is connecting into a dip socket, and it's one of the what I would call cheap dip sockets that are kind of like a spring leaf contact. Those can have issues or develop issues over time. And even though this isn't regularly removed during servicing, I did find that there was a slight improvement when I removed this and cleaned it. It's kind of hedging your bets against the future, really, more than trying to fix an issue, unless this actually is a problem. The leaf springs, when I'm talking about, is similar to this style here on this interconnect here that connects A2 and A3 boards. You see there's a leaf spring in there, that gold leaf. On that dip socket, they're not even gold plated. There's usually a metal shield hiding all of this bottom component here. This is a custom sine shaper circuit chip. That's pretty much a given. That, I mean, if this goes, you're going to have to find another one. Unless you want to reinvent the wheel and try to come up with another type of plug-in board that does the same job as this. In this part of the diagnosis and testing, I've surmised that the sync circuit is faulty on this unit. The signal generator in this part, which is generating two ramps, and then from that generates the sine and the square wave, generate an up and down pulse here. Those go up to this driver circuit here, which in turn generate the external sync that comes out here, and an internal sync that goes down through this connector here. It's an odd circuit, and we'll take a look at that circuit a little later when we go to the schematics and the block diagram tracing out the sync circuit. For some odd reason. They're using carbon comp resistors here, maybe to try and reduce spikes or high frequency transitions. Carbon comps tend to absorb those a little bit better than thin film. So here again is the area I'm working on. This is a tracing down the sync issue on the 3314 scope. This is the first of the 2 units. And what we're looking at here is this area here, particularly this transistor, this resistor here, and this output here. This is the sync going to the internal frequency counter. This transistor here is actually generating the external sync through this circuit here and then going out through here. On the scope, the first channel, the yellow one, is the actual output signal. The blue trace is the internal sync, and that internal sync is actually supposed to be roughly 4 volts peak to peak. The blue and the purple are both on the 1 volt scale, 1 pole volt per division. So we're only getting around half a volt peak to peak on that signal. For comparison, I'll put the purple, or the third channel, on the external sync, and you can see that that value is quite a lot larger. That's going through, as I said, this transistor here, the external sync. All of the emitters are tied together to this constant voltage source that's regulated with this circuit here. The only difference is that this resistance is essentially 51 ohms and this resistance is 33 ohms. When power is turned off and this is measured, this voltage, this current, or this resistance is pretty close to what it's stated on here, 33 ohms. So there doesn't look to be anything upstream that's pulling this down to ground. So at this point, I really have to take a closer look at this transistor and see how it's operating and whether it's actually misbehaving when it's actually under load. I did have the transistor out just for testing it, and both the base emitter and the base collector junctions, diode junctions, look good. There was no shorting or no open connections. Of course, that's only a passive test of the diode junctions. It doesn't really show what it does under load. So the next part will be to remove this transistor again. Out of my donor unit, the second unit, I've actually taken this transistor, which is more rarely used. That is this arbitrary sync. That's only used when the arbitrary mode is running. And so I decided to take this unit, this transistor, out of the other unit, as in hopes that it's being used less hours on it, as it were. And in this unit, I'll put it here and see how it works. I've also devised a simple test to test the diode under load. So I've already noted down, here's the transistor I'm going to be using. I've already put it in this circuit and measured it and determined the HFE for this particular circuit with this particular current load. I don't know what the saturation level of this is. It's going to be fairly heavily saturated, so this number doesn't really mean all that much. Under heavy saturation conditions, transistors don't really have a large HFE. They tend to go down to a fairly low value like 10. However, it does show me that a starting point for measuring the other transistor again. So I'll take that other one out and I'll put it in the same circuit here and see what it does to see if there's any obvious issues with it. So I'll bring you back once I've replaced that transistor, and we can see if it's made any difference at all. So I've replaced the suspect transistor Q403, and that's this unit right here. And I replaced it with the, as I said before, with the transistor out of the other unit, and that was actually this one here. I tested the suspect unit. We'll take a look at that later. It was slightly worse, but it didn't really seem to be that big of a deal. It's just like random HFE numbers that you typically see when you look at a batch of transistors. But we can turn it on now and take a look at, see what happens when we power the unit on. Let's get rid of that glare first. There we go. So power's coming on now. And as you can see, it very quickly comes up, and we have a good internal sync signal. The blue sync pulse is now a healthy height. It's about a little over 3 volts peak to peak. There are no E30 calibration errors that happen when it starts up, and so it looks like the problem with the low internal sync signal is solved just from substituting that transistor. I can change the range of the frequency. It's currently at 1 kilohertz. If I move it up to 2 kilohertz, it'll do a transition into the next range. And this used to trigger an E30 and the signal used to disappear. But I'll try that now. We're at 1870, 1880 hertz, and we're going up through 2 kilohertz. Now, we just transitioned through. The signal just momentarily glitched a little bit. Chances are this has to be recalibrated because it's not. It's been a while probably since it's been calibrated, so it's probably compensating quite a bit as it transitions to the next timing capacitor. Anyway, I'm happy with this. So as I've shown before, this is my reference transistor. This is the one that's actually in the unit now. We measured an HFE of 23.6, and we saw that this thing could pull roughly 90 milliamps through the collector when it was given a base current of about 3.6 milliamps. On the one I tested, same circuit, I just wrote the numbers down here. We are getting a current of 72 milliamps collector, and the voltage drop across the base resistor is this here across 1K, so we have 3.43 milliamps. So the calculated HFE is around 21. So it's a little bit less than 23. Not much difference. However, this one doesn't work, and this one does. There could be another problem with the transistor at a different operating range. Perhaps, maybe, I'm not sure what exactly the problem is. I'd have to put it through a full transistor test to look at the trace curves and see if it is aberrant on some of the base currents. It's hard to tell. I mean, the circuit could be very close to being on a hair trigger. It's a very odd circuit. I don't know if I've shown this before, but I have commented, or I have analyzed this. I've tried to analyze this circuit, and it's a really odd sync circuit. Take, for example, this here. This transistor will turn on and on this arbitrary sync, and it will pull the voltage across this resistor up. But there's nothing on this resistor, as opposed to this one here for the internal sink and this one here for the external sink. So what this is doing is a bit of a mystery to me. I mean, this voltage won't really change that much, and it would have to change in order to actually have this impact this. So again, unless it's actually acting as a current divider, it would have to act in conjunction with this one actively toggling or this one actively toggling to affect those signals. So perhaps it's doing some sort of current division or current switching or ratio metric sort of current dividing trickery to sort of have this imposed onto these two. Anyway, enough said. The circuit is working now, and I'm happy with that. I have to find a replacement transistor for the other unit. So we can take a look at the signals that are now on here. We've seen the internal sink signal with the third channel on the scope. I can look at the with the third channel on the scope, I can look at the other signals, such as the external sink, which we can see here is pretty much exactly or very close to being the same amplitude as the internal sink, just the opposite phase. At the top 2 ohm resistor, we can see that that's a pretty flat line now. There are a lot of transitions, although there are some glitches showing up. Right, you can see them there. That happens as it's transitioning between the two phases, up and down. But I'm pretty happy with that, and I'm going to button it up and concentrate on looking into calibration of the unit and finishing it up. I created a block diagram for the sink circuit because it didn't really have a good explanation in the book, and I wanted like a complete picture of it as it traversed through the unit. It touches pretty much most of the boards. It touches the A1, the A2, and the A3 board as it goes through the circuit. So it's a fairly complicated thing, and it kind of highlights that there is a part of the unit that is really not mentioned very much, and it's key or integral to the accurate frequency generation of the unit. So at the beginning we have the triangle wave integrator here, and that goes into the comparator system and creates 2 pulses as part of the comparator. These are not the waveform pulses, but these are sync pulses that are formed when the waveform passes a threshold on the positive side for this one and the negative side for this one. These pulses also go into the sine shaper and help that to create the sine wave from the triangle wave. This is all on the A1 board. Those up and down sink signals then go into these 3 transistors here, of which I believe it was Q403 that we replaced. Yes, that's the 33 ohm one. There is an arbitrary sink input, and then there's the up sink and the down sink that go into the system. The up sink forms the basis of the TTL sink that goes later on to the A2 board here. And the negative or the down pulse forms the basis of the external sink out circuit here. So from Q403, which was our trouble transistor, we get a TTL sink circuit that then jumps through to the A2 board on that 4-pin penetrator connector. here, and then goes into this circuit here, which is the part that's not really discussed in clarity in the book, but this is actually a frequency counter that's built into the system. So there's a clock divider prescaler system here, and then there's a divide by 8 circuit here. That signal coming out then goes to the A3 board here, which is another waveform clock wave shape generator to generate this TTL frequency here. And this frequency has to be in the range between DC and 2.6 megahertz as required by this counter here. The counter is actually an Intel D8253 programmable interval timer, or PIT. It contains 3 16-bit counters, and it can only run at a maximum frequency of 2.6 megahertz. This is fairly old tech. I mean, this is mid-70s to early 80s technology, so that it's not designed to run at higher frequencies, in which case, you know, in that era, higher frequencies would be 10 to 20 megahertz. And then from then it goes to the CPU. The A30 cal error is really generated by the CPU because it's reading the frequency counter, this counter here, and it's not seeing any pulses coming in. So all of this circuit back to this point is dead. And so that's why this is the circuit that you'd be looking at if you have an E30 error, either on a single range or on all ranges when the system is powered up. I printed out a large part of the manual. Back in this era of HP, the manuals were excellent, and I highly recommend getting the PDFs or printing out some of the pages. I do that because I find it just easier to read and make notes on, and I can have the paper by the unit instead of going back to a PC and looking at that constantly. So at the core, I mean, this is a block diagram for the entire frequency generator, the whole thing. As I stated earlier, at its heart, it's really just two current sources, I up and I down, that are used to sequentially charge and discharge a capacitor C to generate a triangle waveform. In reality, there's actually two differential waveforms that are created. A large part of this circuit is a differential signal system to reject common mode noise problems. That's then buffered, and it goes through a hysteresis comparator to generate the square waveform, and then it goes into a sine shaper to create the sine wave. Then the gain control, which were all the relays that we saw on that small board. The output amplifier, which is at its heart just two high power linear transistors. Then the main output. Off of the hysteresis comparator, we have the sync circuit that we saw previously, going into a sync buffer and then the sync output. Not shown here, of course, is the internal sync system used for calibration. The C here is actually not one capacitor, but a series of capacitors. This table goes through all of the frequencies that are available in the generator through a series of 8 ranges, and the capacitors that are used to create the frequencies for each range. The higher frequencies, the lower frequencies can use an X10 amplification to get those lower frequencies out without having to change the capacitor. Quite a large range here. I mean, it's going from 27 picofarads all the way up to 2.5 microfarads. Going into a little more detail on the integration system, this is a block diagram showing how it's charging and then discharging the capacitor to create the two triangle waveforms. This is a differential amplifier, or a long-tailed pair, as you were. So there is a combination current here of I up plus I down on the emitter side. On the collector side, we have the capacitor that's under circuit. These are switched in using relays. And then the independent I up and I down current sources. These can be skewed, one increased and one decreased, to create a skewed wave triangle output. The skew can be basically to the point where it's creating a rising or a lowering, falling sawtooth waveform. It has an interesting effect on the sine wave output as well. So I just thought that you would be interested in seeing this. It's an interesting theory of operation section in here, so if people are interested in how signals were generated in an analog fashion prior to frequency synthesis, it's a good read. The first of the two units has been repaired, and I'm just going to go over some of the parts that ended up getting replaced on it. So we have the general cap swap, the replacement of the ribbon cables, the two 3-pin connectors here for the linear power regulator transistors, and this little PNP transistor here, which was part of the sync circuit that was mysteriously causing the E30 cal errors. This transistor is actually from its sister unit down here, so I'm going to have to come up with a substitute PNP that I can swap in to fix the second one. I've also started doing some of the calibration for the unit, and it's looking pretty good. So I've created this sheet that tracks through all of the calibration and adjustment steps for these units, and it's looking good so far. I had to make a few tweaks on it, but it's operating pretty nicely. So in the next part, I will probably split the video up into two separate ones here, and we'll start going into the second one. I know the first one was a bit sketchy because I didn't videotape some of the parts of the diagnosis. I just managed to get a couple of the highlights. All of the kind of the grunt work of going through and trying to figure out how these things work, where the problem could be, how to decode what an error is and what it actually means. All of that stuff is really not on tape, and that comprised the bulk of the work on this. If you're not familiar with these units, it's a learning experience for sure. It's not going to be, it's probably, unless it's something that's apparent, it can take a while to figure out what's wrong with these things. So I hope you will join us for the second video when I get it out, and see if we can bring the second one, its sister, back to life and functioning. Hope everybody's doing well, and that's it for now. Take care. Bye.